be talking not really about the source code library, but about the Rosetta database, which is where we're going to store most of the data that we require to run Rosetta. So the database has no standard format. These are all just text files that whoever wrote the code to read this data from the database, generally is a person who wrote the format for the database. There are exceptions, like the Dunbrack library had its own format, and we've written code to read that. But a lot of the database formats were written by the person who needed the data. Some formats are much cleaner than others. And sadly, almost all are cryptic and uncommented. It's really annoying to go through and read and just see a bunch of numbers strewn around when there are no comments or any sort of documentation. So we'll make a little plea here, and this is actually a new coding convention as of last year, that if you're making a new database file format, please tell how the file was generated, specify where the data originated, the references, scientific references, where you got the data in the first place, or how you made it, what the file's for, and the format, like put columns and rows, etc., in your file. So some of the database files do have that, and it's wonderful, and others don't. So the database structure is just a directory structure. There's a main database, and then underneath database you have all these main level directories: scoring, symmetry, etc., 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 chemical, rotamer, sequence. I'm not going to be going through all of these because that would take a year. But we're just going to focus on 3 directories that, from my point of view anyway, are pretty important. But there's a lot of other interesting ones here. So if you're wondering where data is read from, you're going to find it somewhere in this directory hierarchy. So we're going to start out quickly by talking about scoring weight files. So those are going to be in the scoring directory, but then in a subdirectory weights down here. And for whatever reason, Google Slides decided to erase the lines that connected these to each other. But OK, so scoring weights is where the weights for the various scoring functions are stored. This, I think, is the Tolaris 2013 W2S file. Now, this file actually does have wonderful documentation at the very top. It's a huge, long description of how it came about and references and such. But I cut that out for now just to show where the actual data is stored. So after the word methods weights, the format's pretty simple. This reference refers to the reference values for all of the amino acids in the reference scoring method. And these weights, I believe, are ordered by the order that they're listed in the AA enum. In C++, you have these enumerations you can set up that put a label onto various numbers so that you can refer to things by a label as opposed to an integer. And so we have 20 canonical amino acids, so there's 20 numbers out here for the different weights, for the reference energies. All the rest of the weights are listed with the name of the energy method that you would use in the scoring function and then the weight that's applied. So it's really simple to make a weights file. Very easy to generate your own weights file. There's also weight patch files, and that is like, say, for example, this one I think came from docking. So if you want to use the Tolaris 2013 score function, but then you want to tweak the weights a little bit so it works better with docking algorithms, you would patch your score function with a score function patch file. And this is what a patch file looks like. It actually just uses the times equals operator, and you just write the method and then the weight by which you want to multiply the regular weight in the weight file. So these are pretty simple, and it's really handy to know where these are and where to put them when you're creating a new score function. When you do if you're creating new scoring methods, it's a little more complicated because you've got to add values to the enumerator for your new method, and you have to register all those. But that's a different topic. This is just where the weights are.
Do you have a question?
OK, yes.
What's the advantage of using the weights patch file rather than just like updating a new weight file?
So the question was, what is the advantage for using a patch file instead of just creating a new weights file? So I think it's just sort of modularity, and it kind of works on the assumption that you can kind of merge a couple different things together. So I could take the Tolaris function and then take the docking function. A lot of times, the patch will basically do times equals 1 for most things, and it will add on a few extra special methods, like interface, for example, or if you, yeah, I mean, that's the best example I can think of off the top of my head. Is that for docking, you want to have there's a lot of interface scores that you would add to the score functions you wouldn't need for any other case. So it's easier to just kind of patch on those extra weights for those new methods than it is to bother creating a new file. But I think in a lot of cases, both exist. There's like a docking patch, but there's also a docking's weights file that's already applied to patch. So it's just more flexibility, I suppose. Yes?
Does it have to always be times equal? Because if you had terms that were set to 0 in the original
Yeah, that's probably why it's times equal. So the question was, does it always have to be times equal? I didn't check, but I'm assuming you must have to be able to do plus equals. Is that correct, Andy?
You can just set equals.
You can just set equals in that
there
file.
There was an example in the previous slide.
Oh, I just didn't even see it. Okay.
Yeah, FALEC.
FALEC, which is where? Down here. Oh, yeah, there we go. So you do it with equals. Thank you.
have to say times equals 1. If you just want to keep it the same,
Yep.
you don't need to say that it stays the same.
Okay.
You just not have that attribute.
Right. Yeah, they do times equal 1 down here, but you don't have to. All right. Thank you for the clarifications. All right, moving on to the rotamer library. So this is where not only the Dunbrack rotamer library goes, but any rotamer libraries that you might create for your own purposes. For example, the nucleic acid people have a rotamer library in here for the DNA. And those, the folk who've worked on the non-canonical amino acids have their rotamer libraries in here. So it's a good place to just put rotamer libraries in general. The Dunbrack library itself is stored in this extended opt1-5 subdirectory. The data there is actually all stored in zipped files, so you have to unzip them before you can read them. Also, they're so large that, I don't know if you've ever noticed this, but the first time you use these files, there are binaries that are created because of the massive size of the library. So to make things faster, so that's when you first use Rosetta and do any kind of thing that requires rotamers like packing. It takes a while on the first run because it's going to create these binaries. After that, it's a lot faster. A line in a rotamer file looks like this. I'm not going to go into extensive detail, in part because I don't know what all the columns mean, but you have the 3-letter code for the amino acid that's, again, based on those enums. And then you have the torsion angles, phi and psi. And then for an arginine that has phi and psi minus 181, minus 180, you then provide a bunch of bin numbers, side chain torsion angles, and deviations, standard deviations for those angles to kind of, so that's how the library file looks, each line, lots and lots of lines. So then chemical is a really huge folder. There's lots and lots of stuff in there. And it makes sense because the data of all the chemistry is really important for getting things to run properly. And you'll see you have a whole slew of subdirectories. This is where all the chemical information is stored. It consists mostly of what we call sets of types. And these are not C++ types. They're more of the philosophical version of types, or they're abstract classifications of chemical entities. So you could think like I'll give an example in just a second. So for example, a specific alanine that you have in your specific protein is going to have the alanine residue type. There's no reason for you to have copies of all the special data of like the atoms that are inside you and the properties of those atoms, because every alanine has the same atoms in it. They're all the same type. So that's the distinction between a specific residue and then the residue type. So all the residue, a specific residue just has a pointer back to all the data that's in a residue type. All that data gets read from this database, and it's stored in the residue type set. So this is just a set of all the different, so another example would be, we also have the type element, and that's stored in the database, and it's essentially your periodic table. Okay, so a whole slew of them are found here. You have all the elements. You've got orbital types for, sp and sp3. You have various atom types. This is different kind of parameterization. So you have the Rosetta atom types, but you also have the charm atom types, gas diagram atom types, things like the various representations of parameters for atoms are all stored there. Similarly, the various residue types all go here. So this is like, yes?
I was just wondering, if we were talking about the typing platforms, and this would be different residue types, I guess, for the different systems.
Yes.
And then, Rosetta can read that, but doesn't it need to be encoded in the prop every single time, or is it like something that it would recognize as a function?
Okay, the question was that you have cysteine and you also have cysteine. They're really two separate residues. And are they different residue types, and how can Rosetta recognize them? Is that essentially what you're asking? Yeah, and so we'll get to that a little bit. They do have to be different residue types because they're different. One has a hydrogen, the other one does not at the end of the sulfur. And it's how it's recognized varies actually depending on the situation and how it's read from the PDB. But I'll talk about that just a little bit. The various residue type sets come from the fact that you can have a full atom residue type set or a centroid residue type set. And there are some people talking about making it some sort of in-between, something that has centroids for the big aromatics, but full atom representation for everything else. So you can have various types of residue typesets. And then ring conformation, something I've thrown in there for a similar kind of thing. Anyway, so the residue typeset directory is going to focus on the most because it's the most, I think, the most fundamental for understanding how residues make it from a PDB into a pose. So we're going to look at the FA standard example. There tends to be 4 things in each of these typeset folders. So there's a patches folder, a residue types folder, and then a patches text and a residue types.txt. So we'll go through these in reverse order, what they are. So this is residue types.txt. This file is read whenever a residue typeset is instantiated. So when you make a residue typeset, it just reads through this file line by line, and basically it goes to this file, this params file, and it reads in all the data from this alanine params file, and it creates a residue typeset, or creates a residue type and adds it to the set, and it goes to the next line and does it again. So if you're ever adding any new residue type to Rosetta, it's important that you have to add that new parameter file to this file, or it'll never make it into Rosetta. Well, there are other ways of getting in directly, but this is one of the ways of doing it. And then the other point is that a lot of times you'll see people have commented out a parameter file. If it's commented out, it won't get read into the residue type set. So sometimes if you're trying to do something and you're following someone's protocol, they'll actually tell you to go into this file and uncomment a residue type. You'll sometimes see that. The patches text file is extremely similar. This is also used when residue typeset's instantiated. It tells Rosetta which patch files to load. So patch files provide specific instructions to modify the residue types to kind of combinatorially expand your residue type set. And we'll get some more examples of that later if it's not clear. But similarly, you need to make sure you know this file exists so you can put your patch file in here so it will get loaded in. All right, so topology files are also called params files. They end in the .param setting. This contains all the data that's going to make it into a residue type. And so I'm going to go through this in some detail. So the file can have comments. It has a bunch of tags followed by a bunch of data. So we'll go through a bunch of tags. The name specifies a unique name for your residue type. It's not limited to 3 letters. This is really important. There's actually several different names. It doesn't have to be 3 letters, it is in this case, but it can be as long as you want. It just has to be unique from the point of view of the residue type set that you're including it in. These are more what you might be used to seeing. These are the 3-letter code and a 1-letter code. For an amino acid, those are pretty straightforward. This is used for inputting. This must be the 3-letter code that's used in your PDB file, and this must be the 1-letter code that's used if you're outputting to a FASTA file, FASTA file. Type polymer is one of 2 options. You can also have ligand there. And this is sort of a misnomer because it's not really, not all polymer residue types are actually part of polymers. They could be part of oligomers or such. But what we call a polymer in Rosetta is anything that has a lower and or upper residue connection. I think Andrew mentioned a residue connection really briefly before, but it's a special class that tells you how to connect to the previous or the following residue. So if your residue type has connections to other residues, then it is considered a type polymer. Otherwise, it's type ligand. All right, this is another confusing name. We've had like Alice show up 3 times in this file. So the AA refers specifically to the enumeration value that is used in the C++ code for the purposes of knowledge-based potentials. This is not the 3-letter code that is read from the PDB. It's a different number. And the code actually has to be an element that's found in this file. And that limits you to basically, if it's not an amino acid, it's not one of the 20 amino acids, or if it's not a nucleic acid, what you're supposed to put here in your file is unknown. Don't just add any 3-letter code here. This is specifically used for cases where we have knowledge-based potentials, and it's hard-coded into the C++. Okay, so the atom section in the topology file is what actually defines each of the atoms used in the residue type. The first column is the name that you will see in a PDB file. This is the input name. So these have to match what's in the PDB file. These are the atom types that are used in Rosetta. A list of atom types in Rosetta is stored in the database here, database chemical atom types. This tells Rosetta how to Rosetta has its own way of handling all the atoms and its own parameters that it uses for whatever it does. That's all based on this name, like C alpha backbone. The next column are the charm atom types. This is used for any kind of molecular modeling kind of stuff, simulations that you might. The charm, or also they're stored here in the MM atom types, molecular mechanics atom types, but they come straight out of charm. So if you want to know what kind of atom to put here, just load up, what the types are for charm. That's what goes in that column. Next column is your partial charge. The column after that is another kind of partial charge that has just recently been added, so I honestly don't know much about it, but I'm pretty sure it's used for gas tiger stuff. No?
It's parse charges. It's just an alternative form of partial charge.
Okay, so calculate a different way.
Yeah.
Yeah, okay. So there's two columns you have for partial charge. This one is optional. It's been recently added. Sorry about the error there then. Okay, next is the connections. This is a polymer residue because it's an alanine residue. So it has to have lower and upper connections. You define that really simply by saying lower connect nitrogen, upper connect carbon. This tells you which atoms the residue connections are added to. Any polymer has to have that. Okay, then you define your bonds. It's pretty simple. There's a bond between nitrogen and C alpha. This bond type here is kind of an expanded bond. It not only tells you the connection, there's a bond between C and O, but it tells you the bond order. The bond order here is 2. This is also recently added. It'll start to allow us to do some more fancy chemistry. The properties list is a bunch of strings that tell you about the various properties of your residue type. This is used for all sorts of purposes, but essentially every property in here gets eventually turned into a Boolean function, like is it a protein, is it alpha amino acid, is it metal binding? And you can use this in your code to do specific things with specific kinds of families of residues. Like, this code only needs to run if I'm working with metal binding residues. This is how that information all makes it into Rosetta. All sorts of things can be here. And you can see all of them in core chemical ResidueType.cc. So if you're wondering what properties are available, or if you want to add new ones to the whole residue system, this is where you do it. This is something new. It's if you have a metal binding atom, you can define it here. Neighbor atom is the position from which all the neighbor calculations are performed. And the trick here, the trick here is it's very important this atom does not move during packing. Because, so it needs to be like on the backbone and not move around when you do the packing. And then the neighbor radius is the distance that encompasses all of the possible rotamers of your particular residue type. That way, when you pack, all the positions of that side chain need to remain in a sphere that extends out that radius from that atom. And what that allows you to do is that way your scoring works out okay. If it's beyond that radius, you say, it's not touching my residue. This designates the first side chain atom. And it makes a pretty big assumption, and that assumes that every atom before this point in your atom list above was part of the backbone. So you don't actually define your backbones, you just say first side chain atom, CB, everything before that in the list is considered backbone. This is this is used particularly for the FA pair potential. I'm not going to go into too much detail there. And now we get to the final large chunk that's tricky and important, and that is the internal coordinates. These are the idealized coordinates. If you are loading a pose from a PDB, it's going to use the coordinates in the PDB file. However, if you're creating a residue type, creating a pose de novo, it's going to look in this file to find out what sort of idealized initial coordinates it should give to the residue. Also, if you load something from a PDB and it's missing atoms, like almost all PDBs that come from crystal structures are going to have no hydrogens. It needs to look through this file to figure out where to put the hydrogens, ideally. So it's important that these numbers are correct, but it's kind of confusing at first, so we'll run through it. It also helps with the internal coordinate reference system that we use. So the order that you list things matter throughout this file. You want to maintain the same order that you do when the atoms are listed, and you also want to maintain an order that makes sense as far as the atom tree is concerned. That you only connect, you have to make connections, you have to add new atoms by connecting them to atoms that already exist in the tree. All right, so the first column here gives you the name of the atom being placed. All right. The next column gives you the torsion angle with these as your references. This gives you the torsion from the nitrogen to the next 3 atoms. Now, for the first one, that doesn't make any sense. I'll explain how you deal with that later. But if we look down here, carbon beta has a torsion angle of 122 degrees relative to C alpha, nitrogen, and carbon. Okay? The next column, it kind of goes in like this. The next column gives you the improper bond angle, which is 180 degrees minus the bond angle, of the C alpha relative to this column and this column. And then the fourth column gives you the bond length relative to just this column. So obviously, if you don't have any atoms in your residue type yet, all these numbers are going to be completely meaningless, and so are these ones. So by convention, when you define your first internal coordinate atom, you just list the first atom, the second atom, and third atom in the tree, but the numbers don't mean anything. Once you get to the second atom, you have to define 180 degrees, and I'll have a graphic to go through this one more time. This has to be 180 degrees. This is still the same order as these atoms here, and then finally we have a value that makes sense. This is the bond length between your nitrogen and your C alpha. And then now we get to the third atom. The torsion angle is still meaningless, but now we have an improper angle that is actually real. There really is a 68-degree angle between the C alpha, the C alpha, and the nitrogen. And then one more point before I go through and show you a picture of this. You also have to remember in your topology files for a polymer to make sure you define your upper and your lower connection, and that is done by using the upper and lower tag. So this gives you the internal coordinates to get to a point in space where the next residue is going to begin. So that's how that works. All right, here's a little picture. Let's say we're building an alanine, and this comes straight out of that file, and we've built this many atoms, and we're going to start putting on our first hydrogen onto our C beta. So I'm going to represent it now in a line structure. The first thing we do is we extend in a straight line from C alpha to C beta, and then we plop our hydrogen here at a distance of 1.09 angstroms. And you can see the improper bond angle is 180 degrees right now. So that's the first step. Second step, we move to this row, and we say, okay, now we're going to set our improper bond angle. So we move 70.5 degrees from here, which means we're 109.5 degrees on this side. And that makes the angle from hydrogen to C beta to C alpha. Now we finally do our torsion, this column. We swing around 180 degrees from where we were, and now we have a torsion angle going from hydrogen to C beta to C alpha to nitrogen. And now we've finished drawing our molecule for that hydrogen. So that's how that works internally. That's what those numbers mean. Yes?
Can you explain upper and lower?
Upper and lower? Yeah. So here's this is everything goes from nitrogen to N to C, right, in a peptide. So here's this carbon doesn't have anything coming off of it. It's not really an aldehyde. It's actually has a connection here. So we would say that there's an upper connection, and the coordinates would put the point for that upper connection right about here where my pointer is. And that point in the internal coordinates would be where the next residue begins. So when it's building the pose in the atom tree, it would place the nitrogen from the next residue, the downstream residues, it would sit right here at the upper connection point.
The residue should be same to the next residue.
What's that?
The residue for upper
Yes.
would be same as the next.
Yeah, they are the values that will give you a point in space where the next residue will begin. And then when you plop that residue there, its lower connect will give the position for that atom. And that's how they maintain the right torsion angle between them. Okay. So there's a bunch of other tags. I'm going to fly through these really quickly because you can just look at all of them in core chemical residue input-output. There's really, really good documentation that has been written recently above the read topology file function that describes all these tags. This is what reads the params file and calls all the right methods. If you're going to add anything new to the residue type system, please be sure to document it because a lot of work went into making sure that looks nice. Useful tags you're going to see. I gave you an example of alanine. I probably should have used something a little bigger so you could have seen this. But if you're defining the side chain torsions, they are done with this chi tag. You say chi, you give a chi index. So chi2 would be from C alpha, C beta, C gamma, C delta 1. Now this is used for any torsion angles that are not part of the main chain. This is not limited to a true chi. It's really another misnomer. For amino acids, it's a chi angle, but for other things, it might be called something completely different. Nucleic acids they're not called chi. That means something different in nucleic acid terms. However, nucleic acid params use this chi designation for all their side chains. So it really should be like a side chain torsion designation. Connect is like lower and upper connect, but this is for other chain connections that are not main chain. The best example that most people would be familiar with would be connect SG, which you'll see in the cysteine params file. So that means that the cysteine, instead of having a sulfur hydrogen, it's going to have a sulfur, and then it's going to have a connect on the SG. And that, again, has internal coordinates to bring you to the next sulfur across the disulfide bridge. If you use one of these, you need to make sure you define its internal coordinates in that internal coordinates list. And the label you use is CON, N, and then an index where N is a connection number, including the lower and upper connects. So for a cysteine, you would use con3, not con1. So that's really important. If you don't do that, Rosetta does all sorts of crazy stuff, as I learned the hard way. All right, cut bonds are used when you have rings. It has to do with so the atom tree and such things build the graph properly. So if I have, you can't actually make a ring because we're using DAGs. So what you can do is you can define the bond and then tell Rosetta that it's a cut bond. It's like a virtual cut in it. And don't use one without the other. Okay. Then there's all sorts of ways of providing rotamer libraries. For if you're using non-canonical amino acids, you have this non-canonical acid, NCAA lib path, as well as number of rotamer bins. You use those together to read the right rotamer library from the database I showed you earlier. If you have your rotamers stored as a bunch of separate PDB rotamers, like ligands do, then you can provide a list of those PDB files sampling possible ligand conformations. That's another alternative. You use that label. Or for protons, you can actually define the chi angles and the rotamer bins and such for your protons in this proton chi line. So there's lots of different methods you can use for doing that. So what really happens when you create a residue type set, and how does this all get loaded in? Residue types are loaded into the residue type set at the first time you need it, because the residue type set is one of those singletons we were talking about. So it exists in memory one and exactly one time. So if when you're first instantiating a pose and then you load it with a PDB, once the PDB method starts running to load all that information in, it creates your residue type set. When that happens, it reads that residue types text file I showed you later, and it loops through every single params file in that list and loads in all the information. That happens in this function, read topology file, which is, again, located here. So it reads through, sets all the data for the residue types, and then, and basically you now have a residue type that's been instantiated to match the data in that file. But you're not done yet. That only loads like the 20 amino acids and the four nucleic acids for the DNA, and then the 4 for the RNA, and a few others. It doesn't, it's a pretty small set at first. However, I don't know if you've noticed a little message from Rosetta that says you have like 1,500 or 3,000, I don't know however many it is now, residue types when you do this. So what else is going on that expands that? And that's the patch system. So next, residue type set, the code there, reads the appropriate patches text file, loops through every patch in the list. And for every patch file, every residue type currently in the type set is checked to see if the patch applies to it. So it's a very combinatorial expansion kind of thing. If the patch does apply to that residue type, then the residue type is cloned, and then it's modified by the information in the patch file to become a new residue type. Every residue type is a unique individual, but you start out by cloning it and then modifying it to make a new one. Patching only ever occurs one time, and that is when the residue type set's instantiated. So once the entire residue type set is made, patching is done, at least the current implementation of the code. All right, so it's also important to note that a residue type can be doubly patched or triply patched or quadruply patched. So if alanine goes through and it gets patched into, for example, a lower terminus alanine, which is different because you remember it has to delete the lower connection and replace it with some hydrogens and change the nitrogen from an amide nitrogen into a free amine. So that patch is one patch. Well, now alanine, lower terminus, is hanging out in the residue type set, and then it gets thrown in, and the patch file that applies to that for upper terminus can also be applied. So you can have an alanine lower and upper at the same time. This occurs if you had a PDB that just had an alanine all by itself, or if you were loading alanine in as a ligand, it would be alanine, lower terminus, upper terminus. So you can have multiple patches. It gets really crazy. Patch files, I'll go through this much faster than I did the params files. They have a name. This name is appended by a colon to the residue type from which it was modifying. For example, if alanine makes it through this patch file, it's going to become alanine colon N-term protein full. That's the full Rosetta name for that residue type to distinguish it from other types of alanine. In the patch file, there's this types line that now says this is a lower terminus type. This is the type corresponds to a list that you can find in the variant type class. The variant type, variant type file. The variant type is a kind of is a class. It's used for the patch system. Basically, as you'll see later on, there's things down here that say if it's not a variant type lower terminus, then skip. So that's what that's for. That's for designating that now this alanine is now a lower terminus variant. Okay, and again, they are found in this file here, varianttype.cc. You can see the whole list of variants. If you want to make a new variant, you've got to add it to that system. This is a little confusing at first, but the patch files have these selectors, and they have begin selector and end selector, and everything in there is a property that has to apply to the protein, to the amino acid or to the residue type, that you are trying to patch. So in this case, this particular patch only will work if the residue type is a protein, if it's not a lower terminus or any of the other variants. If that's the case, it'll continue. You can also have subcases, and those are designated by begin case and end case. So here's a good one that's well commented. Let's say we want to deal with a case of proline. So we say begin case, and then we have a separate set of begin selectors that say, okay, it's already made it through these checks, so I'm still deciding whether I'm going to patch this or not. And then this begin selector says, okay, is it a proline does it have proline for its alpha-alpha enum? Its AA enum. If that's the case, then it patches it, and it does specific things to the protein. So then after that, you begin the patch operations for that particular case. And these all look very similar to other things you've seen in the params file, like add atom instead of atom, but it's the same kind of column format. Most of them are very similar. If you want the complete list, you can go to core chemical patchoperation.cc and see all the different things you can do to a residue type to patch it. You should also see the documentation at the beginning of core chemical patch.cc for more information about how this all works. And this is that's one of my favorite comments in the code. Totally making these up makes you feel really confident about the science going on here. All right, so that's it for the database. Moving on, so that's about halfway through. Now we're going to talk about some leftover stuff that hasn't been covered unless there's any questions about that. I know we kind of flew through it quickly, but okay. So now we're going to talk about some miscellaneous stuff. So here we go again. You've seen this many times now throughout the presentations, and we're going to focus back on core for a little bit. The four things I'm going to try to highlight are symmetry, task operations, ResidueSelectors, and pose observers. So as anyone who knows biology knows, symmetric systems are very common in biology. Quaternary structures can result in these massive complexes. You have all sorts of really crazy complexes and all sorts of different symmetry states. So if we can reduce the degrees of freedom in our system, we can drastically reduce our search space and explore it more thoroughly. This also speeds up our score calculations. So it makes a lot of sense to have a way of breaking down a gigantic complex into symmetric subunits. And then you just deal with the one subunit and you extend it all throughout with various symmetry operations. So this all lives in namespace course confirmation symmetry. Excuse me. I think this was already hinted at a little bit. There is a class, SymmetricConformation, which inherits from confirmation. What it does is it overrides a lot of the confirmation methods. For example, set XYZ and set degree of freedom is different in symmetric conformation to work with the fact that you're dealing with a symmetric system. The atom tree does work as usual, however. So symmetric conformation also contains a symmetry info object, and this is kind of a class that just stores a bunch of information that is required for doing all the right things to the symmetric system, such as replicating one subunit in a different area of space with the right transforms. So it has there's a whole truckload of information here. I just kind of grabbed some almost out of random, but you can see that, like, for example, number of residues per monomer, or the number of interfaces. This is all stored in private data in Symmetry info, and the SymmetricConformation can access all that. For me, it makes a little more sense to see an actual Symmetry definition file. These files are read into Rosetta when you're dealing with Symmetry, and it tells Rosetta how to handle the symmetry of your system. And so you have like a Symmetry name for the type, the type of group that you're dealing with. This case here has 2 subunits. It has 1 interface. And so this tells you the formula for how do you change the score so that the score is correct for your system. Well, if this is a 2 subunit system with 1 interface, it makes sense that the score is 2 times, this actually represents a virtual atom, but it'll say multiply this score by 2 and then add the score of the interface is what this notation means. And that makes sense if you had a 2 subunit system with 1 interface for how you would adjust the score. There's a lot of information here about anchor residues, how to do the virtual transformations from one to another. Like this tells you the rotation is about the z-axis. And then there's basically Symmetry also uses a bunch of virtual residue types. And these virtual residue types are positioned in such a way that they kind of provide a framework for you to work with the rest of your system. So it's pretty complicated. Fortunately, there are 2 handy scripts that you can use to generate these Symmetry definition files. The one is written in Perl, the other one's written in Python. This guy is used for specific structures. You have a PDB, it's huge and complex, but it's got a lot of symmetry. This will go through the file and generate the Symmetry definition file based on what you actually have in front of you. If you're working in a de novo case, you want to create some complex de novo, you would use this file. So those are the 2 files you would use to generate all this stuff. All right, now move on to the PackerTask. Andrew already talked about a lot of this stuff. This is located in core PackerTask. So a PackerTask is I'll say hand wavy, like a move map, in that it includes instructions about what can or cannot happen to a pose. In this case, we're talking about what can we do or what can we not do during packing and design to our pose. There are 2 important notes that are crucial to understanding PackerTask, and this is very different from the move map. The first is that PackerTasks are, the operations and functions that you do with or to a PackerTask are commutative. That means that the order that you make changes to a PackerTask has no effect on the end result of the task. This is just like in math. 4 plus 2 is the same as 2 plus 4. The order doesn't matter, you still get 6. So if I have a PackerTask and I want to, and I call restrict to repacking, and I call or include current and several other functions to modify my PackerTask and prepare it for everything else that I'm going to do with it, then the order does not matter. So it's important to remember what things are on by default and what things aren't. So packing and design are on until you turn them off. So if you just create a PackerTask, you don't modify it at all, it's going to pack and design everything. So the function restrict to repacking has an and effect with the current settings. So if the old setting was, like I said, it starts off by it starts on at first. So the old setting would be true in this case for whether or not you're going to pack and design something. If I call restrict and repack, it's going to say and false, and the result is going to be new setting false. Do not design, only repack. Rotamers and non-canonical amino acids and other kind of extensions of the things you can pack with are turned off until you turn them on. So most of those sort of functions have an or in front of them. You'll notice that the include current isn't just include current, it says or include current. And that has an or effect. So if the old setting was false, we are not going to include our current position of our rotamers. Then we're going to or that with true, and our new setting is going to be true. Does that make sense? It's kind of a strange thing when you look at it this way, but that's really what's going on. The main point, take-home message is commutative. You can do these operations in any order, and you'll get the same result. That'll be really important when we talk about Task Factory. All right, note 2. I know Andrew already mentioned this. These are specific to a particular pose. So I'll give you 3 examples of why. For one, you can't use a PackerTask on pose 1 and then use it to pose 2. For one, they probably have different residues, different sequences. It doesn't work. You have to use a particular PackerTask for a particular pose. That also means, though, for example, that if you're doing loop modeling, say, and you have an interface, if you've done some modeling with your loop, that means your interface has changed. So if you had a PackerTask that was set up to only pack residues at the interface, if your interface is different, your PackerTask is completely meaningless now. So you don't want to use the same PackerTask. Also, let's say you're doing design. I know Andrew mentioned this one. If you have a pose sequence, you've changed it by design, and then you use your old PackerTask, you're going to undo everything you just did. So we have some solutions to these problems. And one is to use a task factory, and that involves task operations. So if we go back in time a little bit, so our second lab, so we're talking about day 1 of boot camp. If you can remember back that far, you should have done this at some point. It's copied right out of the lab. Well, except that I shortened it with a namespace. Anyway, so you created a PackerTask OP, and then you did that with this task factory. You restricted that task to repacking, so you've modified it, and then you packed rotamers with a pose and your PackerTask. So this works. There's an alternative, though, to doing it that way, and that is to use a task factory. So it's what you do first is there's this class called restrict repacking. Restrict repacking is the name of the class. It's a task operation subclass. Let's call it prevent repacking, and we'll create a new one here. Then you create a task factory. We're going to call it TF. Now, to our TF, we use its pushback method, which reminds us of a vector 1, right? We're going to add a new task operation to the factory. We can add as many task operations as we want, and the order we add our task operations doesn't matter at all because PackerTask is commutative. So we just add a whole bunch of classes, these task operations, to our task factory, and now we have a factory that's ready to build a PackerTask at the moment we need it. And so what we do down here is we say TF, our task factory, create PackerTask and apply our operations to the pose, and boom, we have we're all ready to go, and we can do this. So every task operation has an apply method that takes a pose and a PackerTask, and it basically applies an operation such as restricting repacking to the PackerTask. That's how they work. All right, so why are we doing this alternative? Well, like I've said before, and I'll say again, and everybody else has been saying, unlike MoveMap, a PackerTask is specific to a particular pose, and you want to use it just before you need it. I mean, you want to create it just before you need it. So if we have task operations, we can create a task factory all ready to produce all these different PackerTasks that have exactly the same sort of restrictions and settings. And then we can use them on all sorts of different poses right before use, because the task factory takes a pose, and it will create a PackerTask specific for that pose based on all the task operations that you gave it. So this is really, really handy to use. So some examples of some really common task operations. We have restrict repacking, which we just talked about. It's when you don't want to design residues. Initialize from command line gets your PackerTask options directly from the command line, from the option system. Extra rotamers generic expands the size of your rotamer library. And include current is one that I find really helpful. That includes whatever position is in the PDB file when you load it in as one of your possible rotamers. So there's a whole slew of them, though. OK, and if you want to know where they live in protocols, toolbox, task operations. You can see the whole list of them. All right, so this moves us into ResidueSelectors, which are relatively new, and they're a very handy way of selecting groups of residues, particularly to pass the task operations, but as well as other things. As the code expands, there'll be lots more uses, I think, for them. So they're located in namespace core pack task residue selector. Every residue selector applies its criterion to a vector 1 of Booleans. Its type deft here is residue subset. So basically, if you have a 50 residue pose, you're going to have 50 Booleans that can be set to false or true. If they're set to true, that means they're selected. If they're set to false, they're not. So the index of the vector is the residue position. Okay, pretty simple. An example would be a chain selector. So it implements the pure virtual apply from residue selector, and it also has a set change strings method, and then it stores that in private data. It's pretty simple. It's very light. How would you use this particular example? Well, we'll create two vectors. We'll have a vector of Booleans, and we'll call it set. This is our set of residues. And we'll create another vector we're going to call list of chains. And we're going to make sure the set that we created has the same exact size as our total number of residues in the pose that we want to apply, that we want to work with here. So we've done that. And then we're going to push back the string B and the string D to our list of chains vector. And the reason we're doing this is because we intend to create a chain selector that we're going to name select chains B and D. So we've now created select chains B and D. We're going to call its little method set chain strings, and we're going to pass in our list of chains, which includes B and D. And so now select chains B and D, when we apply it to a pose and we hand it our vector, it's going to take that and it's going to set every residue that's in chain B to true and every residue that's in chain D to false. And so that's how these work. Does that make sense? Okay. So there's a large assortment of available selectors. We have a chain selector, we've got residue index selector, we have interface group by selector, number of neighbors selector. There's a whole lot of these, and it's easy to make a whole bunch of them for whatever purposes you have. There's also logical Boolean operator selectors. And so we have an and residue selector or not, right? So the Boolean residue selectors have constructors where you can just pass in two other residue selectors. So in this case, let's say we made a select chain A and a select residues with 3 neighbors as our residue selectors. Well, this residue selector will AND those two together. So essentially, we're going to get select chain A residues with 3 neighbors. And then we can apply that to a pose and a set, and our set will now contain trues and falses corresponding to whether they, are in chain A and have 3 neighbors. So very powerful and versatile. Yes?
Can you pass these as command line flags?
I have no idea, actually. Andrew? It's your baby.
You should say Rosetta scripts in the XML file.
Yep.
The documentation is with the Rosetta scripts.
Yeah,
Yep.
but not from a,
But now there's nothing that would be.
Yeah. So the question and answer was that can these be called from the command line? The answer is not directly, but you could use XML. This is completely works with XML, all the residue selectors and the task operations. So you can use Rosetta scripts very easily with this. So another really cool thing about this is that there's a task operation, going right back to task operations, called operate on residue subset. So it's a task operation class that takes 2 things. It takes a residue level task operation and a residue selector. So this makes the most sense by example. So here we go. Operate on residue subset is this class I was telling you about. We're going to name this prevent repacking of chain A. Not of everything, but just of chain A. Well, the way we can do that is we construct it using its constructor. We give it the prevent repacking task operation that we generated a little higher up in my code, and we give it select chain A, one of my residue selectors. So then you now have this special task operation that's customized to work on a specific set of residues. So this is why this is so cool. Now we can create our task factory, push back our task operation, and we get our PackerTask ready to go, only to repack everything except chain A. Okay, any questions on that? All right, the last thing I'm going to talk about is pose observers. So pose observers are a way to monitor changes in an object's data that we call events and respond to that. There's a couple examples I'll talk about here. One is a Primal observer, which has observer in the name, and then the constraint set. And you're like, well, a constraint set, why is that an observer? It doesn't say observer. But anything can do observing. You can make any class you want observe some other class. So this is more of a way of setting up observation than it is like a observer inheritance kind of thing. So the Primal observer pretty much only observes and then spits stuff out on the screen for you to see. The constraint set, it's really important for it to observe changes in the conformation so the constraints can change numbering as they need to. How does this work? So both of these classes contain special methods to attach themselves to a pose or a conformation, respectively. So for example, the Primal observer has an attach method, and you give it a pose. And that is the pose, so I'm going to attach myself to this pose, essentially, is what this is saying. So here's my reference to the pose. So you call the pose. The pose then has a method inside of it called attach general observer. And what you're passing that are 2 things. This is kind of strange. We haven't seen this yet, but this is a reference to the function general event. So this is a function pointer that you're setting up here. Then the second thing you pass it is yourself. So this, in this case, this is a pointer to the particular instance of the Primal observer that is being attached. So they both look like that. Same thing down here. This attached to my pointer is, oh, there we go. Attached to confirmation calls this attach length observer. It it passes in a reference to this function on length change, and it passes itself. This will be a little more clear later when I show how it's used. But that's how you set up the pose observer from the thing doing the observing. OK, now whenever a length change in confirmation happens, for example, in confirmation, there's a method insert residue by jump. So if anything calls insert residue by jump, the length of your pose has changed because you just inserted a new residue. So inside the code, within confirmation, inside this function's code, at the very end, it says notify length observer of this length event, which includes a bunch of information like the kind of length change, the sequence position, etc. So notify the length observer. So that's what it does. That line is in this function. So at that point, what notify length observer function does is it simply calls up whatever function pointer is attached to it. So it looks through the private data of confirmation, which was set when you did the attaching on the previous slide, and it says, OK, I need to make sure that since that I need to notify all the observers. And it looks through the list of observers and it says, OK, I see that I'm being observed by constraint set, so I'm going to call up constraint set. And then I was told that when I call constraint set, I need to run constraint set's on length change function because it was given the function pointer. So it does constraint set on length change. So actually, a better way to think about this is not really so much that constraint set is observing the pose, but it's more of like constraint set signed up for a mailing list from pose. So that whenever pose does a certain thing, it calls up constraint set and says, hey, it's time for you to do an on length change function. So that's kind of how it works. And when that happens, we're now back in constraint set. Constraint set, when it gets the call from the pose, when the pose is actually running its function here, its on length change happens. That remaps all the residue positions. So that if you've just, if you used to have a constraint that was for residue 10, but you've now inserted a residue, now residue 10, the constraint for residue 10 now applies for residue 11. It's a very powerful tool to have these observers, and there's lots of them throughout Rosetta. So that's how that works. Any questions?